Continuation of videos for class 1 with this statics review, and we're doing shear moment diagrams. I'm going to do 2 examples, and so let me switch over to my camera view here, and we'll do a very simple problem. Now, no pun intended, but it is a simply supported beam, so I guess that makes it more likely to be simple. Okay, so we have this loading of 9 kilonewtons and 5 kilonewtons in these supports. So this one's already set up, but we would draw this free body diagram and then draw these dashed lines underneath it and try to focus. There you go, focus. And so one of the first things we want to do is find these reactions, and we do that by taking the sum of the moments about O. We could have done it actually. We could find this one first if we wanted to. I'm going to change these names to ROY and RCY right there. I kind of like doing that. So I'll find the sum of the moments about O, and if I'm going to be exact, I'd say it's OZ, right? Because it's in the about the Z axis that we're taking it about at O. And I'm going to start from left to right, and so this one, of course, doesn't show up because we're taking the sum of the moments about there. So we'll start over here, and that's going to be 9 kilonewtons times 30 millimeters, right? So we have kilo and milli, so they kind of cancel each other out. So I'm going to go ahead and use them that way. A lot of times I'll use newtons and meters just to keep the base units, just to be careful. But here, I'm going to make an exception. Just makes life a little easier not using so many decimal places out. So, and we note that at about O, this is going to be clockwise. So that's going to be negative because we defined counterclockwise as positive right there, right? And the surface I'm writing on is just a little rough, so maybe I'll put a piece of paper underneath it. Make it a little neater looking. Okay, so we have negative 9 times 300. And then going over to the right, we see we have 5 kilonewtons. That too is going clockwise about O, so it's also negative. But now its distance is 300 plus 900, which is 1200. And then keep it going to the right, and we have our reaction, RCY, and that's going counterclockwise, so it's positive. We go RCY. And the distance to that point is 300, 900, 300. That's 1,500 millimeters equal to 0, RCY, right there. I could show you me doing the calculation of it, or you could take my word for it. That's 5.800 kilonewtons. Right, because I used, the millimeters here will cancel each other out. So the units of the forces here was kilonewtons, so the answer's in kilonewtons, right in there. All right, so now I want to find this other reaction. We also take the summation of moments, by the way, about C, and then find A, O, if we want to, ROY, R-O-Y. But we also can take the sum of the forces in the Y direction equal to 0. And say that's going to be upwards for us. So we say ROY, ROY, minus 9, minus 5, and then plus 5.800. And we end up with a ROY equal to 8.200 kilonewton, right? And you can also check this by, these are both upwards, right? So 5.8 plus 8.2, that ends up being 14, right? 14 kilonewtons. And you can see that 9, these are both downwards, 9 plus 5, that's both 14. So it makes sense. They're distributed this way. So if we want to do the shear diagram, it's good practice maybe to also, we put the V next to there, but we also, when I remember to do it, put what the units are that are on there. I'm going to use kilonewtons just to make it a little bit easier. And so what we find here is we want to pick like just a distance that's kind of proportional. I'm not quite sure what the other numbers are going to be yet, so I'm going to pick like right there. So I'm going to say, well, this is constant between here and here, and it's going to be 8.2. Is that right? 8.2 kilonewtons. And so I like to color that in. And then there's going to be 9 downwards. So what we'll find is that if we take 9 and subtract it out of 8.2, we get negative 0.8. So that's going to be a really small number, and it's constant all the way across from there. So we get a negative 0.8, right? And then we take this 5, and it's coming downwards as well. So that's also negative. So it ends up like being right there. And we get a negative 5.8, right? So that 5 went downwards. It was already negative, so it's a negative 5.8. And then it comes and it meets this guy who's equal to 5.8, which brings it back up to 0, right? That's the thing that's like a test for us to see if we did all of this correct right there. If we did that wrong, if it doesn't come back up to 0, you did something wrong. All right, and now we get to the moments. All right, so what we want to do is we're integrating this, which essentially means the area, right? So we want to find what the area is. So we take 8.2 and multiply it by 300. Now, just to make life easier for us, let's say that these are going to be Newton meters, because that's usually what we want to report moments in anyway. So we're going to take that Newton meters. So this is actually going to be 300 millimeters times 9 kilonewtons, and the kilo and the milli, they knock each other out, right? So this is going to be 9 times 300, but we know that we're going to get Newton meters because we had the millimeters and the kilonewtons. So we have 8.2 times 300. And that comes out to 2,460. 2,460. And so I'm going to pick that right there and write 2,460. And it's positive, right? Because it's above this. So that's a positive area. And so we'll draw that in. And I like to put little cross hatches in there so it can really catch your eye and see what that looks like. All right. So now we want to figure out where this next point is going to be. We have 2 ways to do it. We could do it both ways and double check ourselves. The second way is actually the easier. We'll go the first way, which is because we're going to go from left to right. That would be like I'll call it the first way to do. And it's a little bit more, it's got like an extra step in it. It's not that hard to do, but it's maybe it's good to do this and then check it with the second way, right? So we noticed that this went upwards because it was a positive value, but this is negative. So we're actually going to subtract this area from that value. So that's going to be negative 0.8 times 900. And so 900 and 0.8, that comes out to 720, but it's negative 720. So what we do is we subtract 720 from 2,460. And if we do that, we end up getting 1,740. Right? So it's not that much smaller here, so kind of proportionally, and we'll see that it's kind of going down right there, right? So there's a little bit of a downward slope of our 1,740. Now this next part of it needs to go back to 0. And you go, why is that? Because these are pinned joints, these simply supported joints, and they don't support a moment. It's just it's free to flex. Like if this was right here, it would be a free to flex. This would be like pinned right here, and it's allowed to bend as much as it wants to at this place right there. So these joints don't support a moment, so it has to be 0. Which gives us the other way that we could find this value is to just take 5.8 and multiply it by 300. And if you go 5.8 times 300, you end up with 1,740. You can't see my values right there because of a reflection off of the screen right there. But so that's actually an easier way to find that value, or you can check it, right? But anyway, those are the results. And we see that right here is actually where the maximum moment is going to be. So that's where the most amount of bending stress is going to be. And so if you want to know the shear or the moment at any given point along this beam, like if we just picked a point like that's like right here in the center, right here. So let's say that, because this is 1500, let's say that's 750 millimeters from this end, that's the location. We would say, well, we could even just draw a line down through here. And we'll say, like right there, the shear is 800 newtons, right? Because this is 0.8 kilonewtons, right? And it's indicating that it's a downward shear, if we care about the direction. And then right here, we could go ahead and figure out what that value is by multiplying 0.8 times this distance, which is going to be, what, 450, and then subtracting it from the 2,460, and then we'd be able to find out what the moment is. So if someone asks us what's the moment in the center of the beam, that would be what the answer is. And then we could also go through and figure out what the stresses are at different locations along the beam. I mean, because the beam also does have a thickness to it. So we could figure out what the bending stresses were here. The shear, actually, we'll talk about that in the next class. That's a transverse shear, and that actually has a maximum in this along the center line right there. But we'll cover that. It's called beam shear or transverse shear. Hopefully you'll remember some of that. All right, so here's a more difficult example. That was a pretty straightforward example. This is one that's got a lot more to it. We're really not going to do many of these. It doesn't really, this type of scenario comes up more in like civil engineering where you have distributed loads. We don't really do it too much, but we could. We don't know what we're going to be working on in the future, and we might want to be able to use these techniques. So one of the things I would have changed in this is I would remove these things because I don't want to show the connections in a free body diagram, which I want this to be. So we're just going to pretend it's not there and show the reaction arrows that are right here on top of them, right? And so that's going to be our RAY. They've already labeled that as A. Let's label this as Y. And let's also label this as X. We'll just pick the center of it, right? But just ignore the thickness of the thing. And that's going to be our BY, right? And we'll draw lines down. Sometimes I'll do a dashed line right here. I'm just making them lighter lines. And we'll label the shear as capital V, and we'll label the moment as capital M. And then the first thing we'll do is we'll find what these reactions are. Let's find this one first by taking the sum of the moments about A. And actually, technically, because this is X and this is Y, we're taking it about the Z axis, the axis coming out of the page. So that's going to be technically correct right there. So when we have distributed loads, it's best to try to, I think, to instead of doing it all in one line, which many people do, I just go ahead and figure out what the equivalent load of this across this span is going to be. Because this is distributed evenly, it's going to be in the center. If it had a linear distribution, it would be at the 1/3 thing, just like the centroid of the triangle. This is the centroid of this rectangle right here. That's where that's going to be. And so I'm just going to superimpose it right there. So it's going to have a single value that we're going to pretend that, and we're just using that to get the reactions. That's the only reason why we're using this. And that's going to be 20 kilonewtons per meter distribution across that 3 meters. So that's 20 times 3. We could do that in our heads. It's going to be 60 kilonewtons right there. And then we have 10 kilonewtons per meter across a 1 meter span. So we're going to have right in the center of this, we're going to have 10 kilonewtons. Right? We're going to remember that that's just there to help us as we're trying to find those reactions. That's the whole purpose of us doing it down there. All right, so come on, focus. Thank you. And so moving from left to right, we get to here, and we see that that's going to be clockwise. So we have a negative 60 times this distance, which is 1.5. And then moving over here, we see that this one's going to be counterclockwise, this reaction. So it's positive RBY, and its distance is 3 meters. Moving on to the right, we see we have 10 kilonewtons, and that's going to be clockwise, right? It's going to go this way. Whee! So we have negative. And then its location is going to be 3 plus half of this distance, which is 0.5. So 3.5. We don't have enough room right in there, so I'm going to come over to this one. This one's once again clockwise, and that's 15 kilonewtons. And its distance is going to be 4, right? Equals 0. And we find RBY is going to be 61.67 kilonewtons upwards, right? Now we get to find this other reaction by taking the sum of the forces in the y direction. And we have RAY minus 60 plus 61.67 minus 10 and then minus 15. And we get RAY equal to 23.33 kilonewtons. Easy enough. That's just statics, getting the reactions. Want to make sure you get those. I have people sometimes near the end of the semester still can't do this, and I got to tell you, that's a no-go, right? I got to make sure you're able to do this, right? So we got to get lots of examples and try it over and over again until we really own this. All right, so right here, this is the 23.33 kilonewtons, and so we want to start out right there. So 23.33, and I'm going to write this as kilonewtons. So I'm going to go kilonewtons. I'll remember to do it. And we're going to go, now we're going to ignore that 60, and we're just going to look at this 20, right? So this is going to be a linear distribution, and it's going to be a downward sloping because it's negative right here. So we're going to find this area. So we have 20 times 3, so that's going to be a negative 60. So we're going to take from this 23.33, we're going to subtract out 60. And what we end up with is a negative 36.67. So that's going to be the point that we get meet right down over here. So it's a negative 36.67. And I might want to change my mind about where I want to put this. I might want to wait right here. That's going to be, might get in my way. Now, we have a couple of things going on right here. We have this force is going to be a point load, and it's going to go positive, so it's going to bring us up. How much is it going to bring us up? By 61.66. So if you add a positive 61.66 to our negative 36.67, you get positive 25. 0.00 actually. Right, so we're going upwards right there. And now, what we could do is we could take our 10 kilonewtons and multiply it by 1, and it's downward, so it's negative. So we have a negative 10 added to the 25, and we get 15. Right, so we actually come down to over here, and it is a slope like there. Once again, it's a negative slope. You could see. And then we also then we have that 15 coming down that brings us back to 0, right? So I'm going to color this, hatch this in because I think it's easier to see, to make out what's taking place. And then this is 15 right here. Okay, so we might want to know where that location is right there. In fact, I'm going to make my moment line again right in there. M. I might fix these a little bit. There you go. Yeah, didn't mean. Okay. And what's going to happen here is, look, notice that it gets large, and then it starts to get smaller. Right? It starts out large and it gets smaller and smaller until it gets to 0. This is going to be an inflection point, right? So this is going to be a parabolic that starts off with a big slope, and then the slope starts to become 0, right? So it's going to look something like this, like I've kind of like sketched it really light. But then it's going to be parabolic, and it's going to start to dip down, right? And it's going to go. Now, you might not know, does it get down below this line and this line? Well, we could start messing with the numbers, or we could go from the right-hand side. And quite often, that's the easiest way to do it, is to go from the right-hand side. So first off, we see that we have, this is all positive here, and then it's going to come down to 0. It's got to be 0 here at the end, right? Because it's right here at the end, this thing's just hanging off into space. There's nothing that would create a moment or support a moment, so it's got to be 0 here at the end. We know it has to be. And then it has to be negative over on here, because this is all positive, right? So this is all this is going to be parabolic, and it's going to get smaller as it gets over to there, right? So it's going to start like that right there, and then it's going to get steep, something like that. That's going to be what the thing looks like. And this value is going to be equal to the area that's within inside that. And you notice that's a trapezoid, right? To find the area of a trapezoid, you take the average of the two legs right here, and then multiply it by this width. So it's 15 plus 25 divided by 2. That's 20, right? 20 times 1. Right here. Now these are kilonewtons and these are meters. So the answer to this value right here is actually going to be 20,000 Newton meters. I think it's better to put the Newton meters in there instead of the kilonewton meters. All right, you can. It's not going to hurt anything. So I'm going to go negative 20,000 Newton meters is going to take place right there. So now we could say, from here, as I previously mentioned, we're going to come upwards, and it starts out with a high slope, and then it starts to get to a 0 slope, and then the slope starts coming downwards, and it starts to get slopey. So right there, right? That's what the thing is going to look like. And if I was to color it in, hatch this stuff in right here, that's what that would look like. And now we probably want to find what this value is. In order to find this value, we need to know this location, right? Because we want to know the area underneath that triangle. So in order to find this, all we have to do is find out what this value right here has to go to 0 because of this distribution. So we could say that 23.33 is going to be equal to 20 times some value. I'll call it x, maybe x1. We do that x1, and we get that it's going to be 1.167 meters, right? So this is 1.167 is that distance that it had to be to get to right there. So this value right here is the area of that, which is a triangle. So that's going to be 1/2 times 23.33 times 1.167. If we do that, we get 13.610, but remember these are kilonewtons, and this is kilonewtons, and this is meters, so we get 13,610 Newton meters. We might, for some reason, want to find this point. There's a little bit more work that we have to do. We'd have to apply some logic, and maybe somebody would ask you that in another class. But we're really just implementing these ideas, so I'm not really going to bother with trying to find that. It's not terribly difficult to do. I think what I would do is to use this value right here and then try to find what this would need to be in there. That might be a little bit more of a challenge. And I have it written down somewhere where I did that. But I'm not going to do it right here. I don't want you to get too bogged down. This is more the concept. The thing we really care about is that value and that value, because that tells us where, the moments, the maximum moments. So right here, this is the maximum moment, even though it's negative right here, and it doesn't matter to us. It's just going to decide whether the top or the bottom of that thing's going to be compression or tension. But we could see that that's the location where the maximum moment is going to be. So we might, if this beam is uniform all the way through, that would be the location where we would use this moment to decide how big of the cross section needs to be. So, that's a refresher onto the thing, a couple examples. You working through some more yourself is going to help organize your brain, get you to understand and know what you need to do in order to tackle these types of problems. Now, most of the types of the problems that you're going to have to do are like this. Right, this is for us because we're going to be applying it quite often to, like, let's say a shaft, a shaft supported by bearings. Which I have like a little display unit right here of this little thing that I like to show. So let's take a look at my 3D shaft model right here. So what this is supposed to be is a reducer right here. It goes from a little gear to a big gear. And so if we want to find the stresses that are inside this shaft right here, we're going to see that there's forces of this gear pressing onto this gear, and then also, okay, because this one drives this one, so it's pushing downwards. There's also an element of it pushing inwards right this way. We'll talk about that some more. But then this one is driving this one, so this one is driving this. So these are separate. This is an input shaft and an output shaft, and here's an intermediate shaft that has two gears on it, right? So this one has just a simple single gear onto the thing, and by turning this crank, it drives this gear, which is attached by way of the shaft, and drives that gear. This gear drives that gear, and so this is the output shaft right here, right? And they're supported by bearings. These are what we mean by the bearings, right? And we pretend that these don't support any kind of moment, and to a certain degree that's true, right? It's not gripping it hard, it's kind of letting it be pivot just ever so slightly, but that's enough that for the amount of displacement that's taking place there to pretend that this is a simply support. All three are simply supported beams, but the more complicated one is this guy right here. He's the shaft that has a more complicated loading scenario. So we want to look along the length of the shaft, as we're assuming we ignore the gears often, and we just take a look, and we want to try to figure out, where it's loaded the most moment. Chances are, most of the time, it's at one of the gears. We don't necessarily know which one when we're starting out, but over time, we can probably try to make a get. We could probably see a trend of things happen, because we're going to do this problem over and over again. And what you're going to tend to see is that's one of the places is where usually there's going to be the most amount of stress. And we'll do that and be able to predict where this thing is most likely to break, and then we can decide how big we need to make it. Now, once again, notice that this is called a stepped shaft, so it has different dimensions along the length of the thing. So that's to save material, but also so it has the gears have a place to positively land, right? So now that's exactly the location of the gear, so it can line up with the other gear. If the shaft was the same dimension all the way along the length of it, you'd have to have something that would force the gears to be exactly where, like, we call it a collar. But anyway, we're going to learn a lot more on this. I just wanted to bring it up now in this video, and I will talk about it more in class. So I'm going to do one more video that's going to talk about torque, right? And then, because that fits into the statics review. So that's it for this video. And how long did it show up? It's 28 minutes. That's a little longer than I like, but hopefully this will help somebody, and I might refer you back to this video. If you're struggling through the semester with shear moment diagrams, I will maybe refer back to this, and we can have, and then of course you could always come to office hours and we'll work through problems together. Thank you.